Hello everyone. In this lecture, we will continue our discussion on Denoising Diffusion Probabilistic Models or DDPMs. The last lecture focused on the theory of DDPMs, where we looked at how exactly are diffusion models trained. The theory was quite interesting, and we had a forward diffusion process, and then we had a reverse process, which our neural network had to learn. My experience with diffusion models has been that the theory appears very interesting, but you cannot truly understand the underlying concepts unless you supplement it with a practical example or multiple practical examples. Through the practical examples, we will get a firm understanding of the theory, and it also gives us a chance to nicely revise the theory. So, in this lecture, we will be following an interesting approach. We will take an example, a practical example, and we will exactly see how the DDPM method is applied to that practical example to solve the project. And in this process, we will revise the theory that we have covered in the last lecture. It will also help us to get a intuitive understanding of why the theory works, and our internal confidence will also increase in the process. So let's get started. Before we move ahead, I want to make a quick analogy. The diffusion process that we are studying in these couple of lectures is very similar to how particles diffuse in air. In fact, the theory of diffusion is well documented in the field of physics. Imagine, let's say, you spray a perfume in one corner of the room, and then the particles slowly diffuse, and the smell percolates in the room. This is because the particles are transferring from one corner of the room to another. And another example we can see is that of sugar dissolving and spreading in water. Both of these are examples of diffusion processes. And what is common in both these examples is the structure slowly disappears and things become uniform and very noisy over time. So, what we do in DDPM is that, remember, in variation autoencoder, we had an encoder and a decoder. In this case, our structure is the same as that of a VAE, but instead of a encoder being a learnable encoder, we have a fixed encoder. And the encoder takes the input image or the input data samples and converts the input image into noise. This is not done through a single transition, but it is done through a series of transitions. And then there is a reverse transition process where you take the noise as an input and you construct the image back from the noise. This is called as the reverse transition process. Now, how to construct the image back from the noise is where the heart of the DDPM theory lies in. And it turns out that the final prediction or the final conclusion is that if you want to generate images which are sampled from the true distribution, then you need to predict a noise epsilon hat which is as close as possible to the real noise which is added in the forward process. This sounds very intuitive to begin with, right? But when you actually start doing the mathematics, this is not very apparent at the beginning, and we only come towards it in the very end. Now, exactly this noise is added at what time step, how to compare these two different noise levels. It is hard to explain all this in theory. That's why I thought of having this separate lecture so that we take a nice practical example. Okay, so the example that we are going to look at is we are going to train our first diffusion model to generate images of butterflies. So let's start understanding the different steps gradually. Step number one is the setup, where we install all the key files. And here you can see I have installed a library called diffusers. Diffusers makes it easy for us to execute the code and the forward and the reverse transition process. I will explain that in detail once we come to it. But using some simple lines of code, we can execute our kernels very well using the diffusers library. That is why it is very valuable, and people use it quite commonly for coding diffusion models. Okay, so next what we have to do is we have to go to Hugging Face. We have to go to Hugging Face, and we have to create an access token. So this is a process which is quite simple. You have to go to Hugging Face, go to tokens, and then you can create a token with a read and a write permission. It looks something like this. Once you have the token, you can run this command to log in using that token. And this is something which is you need to install the git lfs to upload your model checkpoints. Okay, so in this code block, we have defined a few functions which are going to be useful for us as we move along through this notebook. Let's try to understand what these functions are doing. The first function that we have defined is called show images. So what this does is, given a batch of images X, it makes a grid. So you basically see the images in the form of a grid. Okay, so this is just a manipulation trick. Given the images as an input, it's a way of displaying the images in a different format. Okay, so the second is define make grid. Given a list of PIL images, stack them together into a line for easy viewing. So what this does is that it stacks images as a single line as opposed to converting them to a grid, which is happening in this function. We will see exactly how these functions work because we are going to use them in some of the subsequent cells down below. Okay, up until now we have not done anything with respect to diffusion yet. We have simply been installing libraries. Notice we have imported numpy, torch, torch.nn.functional as if, matplotlib, and from pil import image. These are the packages which we have imported for this code. Okay, now what about the data set? Remember the whole objective of DDPM, and in fact, this course is to learn deep generative modeling, which means that we will be given a true data distribution, P data. In fact, we will not be given to true data distribution. We want to predict the data distribution, which is P phi of X, which is as close as possible to the true data distribution. And all we are given are samples which are drawn from this true data distribution. Uh, that is the whole problem statement that we have in our hand. Now, in this particular notebook, the samples of data are collected from this link. Let's go ahead and click on this link. It is a data set which consists of images of butterflies. Now, I think there are around 1,000 images over here. If you go and search this dataset, you can see there are 1000 rows in the search column. And this is how the images look like. Okay, so this is the dataset that we'll be working with, a collection of 1000 butterfly pictures. And once you run this code, in this code, what we'll be doing is we will convert these images into 32 pixels. So you can see the image size is 32, and you're transforming each image into 32 by 32. So you're resizing each image. This is very standard in machine learning pre-processing step, where we have to make sure that every single image in the dataset carries the same dimension, which becomes helpful for downstream processing. Okay, and then the next step that we do is we do a random flip, and this is just done to augment the data, and then we do a normalization. So all the pixel values are mapped to -1 to 1. And if you run this, you will see that we have divided, we have first of all got the data. I don't think the train test split is done over here. Okay, and then we are serving the data in batches. So you will see the batch size is 64 at a time. So at a time, 64 samples will be processed in one single batch. Okay, let's go ahead. If you just sample some of the images, so here we have, you see, we have used this show images function. So show images basically displays the image in the form of a grid, and here you can see that we have uh, displayed the images and right, yeah, the shape is 8, which is number of images, and 3 means every single pixel has 3 channels RGB, and the pixels are 32 by 32. That's why the shape comes up like this. And here we are simply resizing for better viewing. So you can ignore this for now. Just focus your attention on this code where our train data loader is basically containing all these images of butterflies. Okay, so next comes a very important step where we define the scheduler. Now, first of all, what do we mean by a scheduler? To understand that, we need to quickly revise our forward diffusion process. So, remember that in the forward diffusion process, what we do is that we have a number of these diffusers uh, which transform the image slowly, and the final image which you see is that of noise. And every single transformation here is a Gaussian kernel that we apply with a specific mean and variance. Now, we had looked at this in quite some detail to understand how these mean and variances are designed, but I'll just give you the final gist of it. So, finally, what happens is that let's say you have this image, okay, which you want to transform at each step, and let's say this image is defined as uh, x0. Okay, the way you write x1 is x1 is equal to alpha 1 times x0 plus beta 1 times epsilon, where epsilon is a random variable which takes a value between 0 and 1. Now, this term, this entire term essentially means that we are sampling from a Gaussian with a mean of alpha 1 times the mean of x0 and a standard deviation of beta 1. And we do this for all the subsequent transitions. For example, x2 becomes alpha 2 x1 plus beta 2 epsilon. And you see here this epsilon, this is the noise that we are adding in the forward diffusion process. And alpha 1 and beta 1 are, they have a relation. They are related in such a way that their square is always equal to 1. Now, in the literature, what we will commonly see is, let's say we call this alpha 1 square as p and this beta 1 square as q. So you can rewrite the above equation as x1 equal to root p q plus root q, sorry, root p x0 plus root q times epsilon. So this is how the equation looks like, root p of x0 plus root q into epsilon. And now you can further simplify this by writing, by using this equation, that alpha square plus beta square is equal to 1. So p plus q equal to 1, and which means that q equal to 1 minus p. So you can write this expression as x1 is equal to root of p x0 plus root of 1 minus p epsilon. I know this is a bunch of mathematical trickery, but this is the common notation which people use in the literature. And what they further do is that this p is replaced by another symbol which is alpha. So they write the expression which looks like this. And I'm just explaining this to you because you will see this notation very familiar, and I don't want you to confuse it with whatever we were initially starting out with. It is just a matter of using different notations, but fundamentally, both of these representations mean the exact same thing. Okay, now let us understand what this scheduler does. Okay, so you see here, what we are doing is from diffusers, we are importing DDPM scheduler. And then we are defining one more quantity which is noise scheduler equal to DDPM scheduler, and in the bracket we are writing the number of time steps. So this DDPM scheduler takes care of the entire forward process for us. And let's try to understand what happens. So all you need to do is to create the forward transition process. You need to write this one equation. So let's understand that. So in this line we are plotting plt dot plot noise scheduler dot alphas dot comprod dot cpu, and we are taking a root of that. And in the second plot we are taking a square root of 1 minus whatever this first quantity was. Now this is something which is uh, the cumulative mean and the variance starting from the first time step to anywhere in the uh, in the forward diffusion process. So let's try to understand, or before even understanding this, we will see how the noise scheduler works. So okay, just forget about the last piece of code for now. Try to focus on this. Time steps equal to torch dot line space. 0, 999, 8. So what we are essentially doing is that we are creating 8 time steps between 0 and 999. And the second line is important, torch.random like xb, which means that we are creating noise values for every single pixel in this image. So you see here the noise tensor looks like this. Now let's try to understand what this noise tensor essentially means. So imagine that you have this image, right, which is 32 by 32 in this case. And in the forward process, we had discussed that we have to specify a noise. Now, this noise, the dimension of this noise is same as the size of this image, because we are adding this noise to each of the pixel in this image. That is why here you see the shape of this is xb, which is the shape of our image itself. And once you define the noise, you can simply use the noise scheduler which you created using the DDPM scheduler, and you can say noise scheduler dot add noise, and you can pass the initial input image, the noise values that you want to add, and the number of time steps. Why is the number of time steps important? Because you need to tell the package how many steps you want to carry out in the forward diffusion process. For example, when we did this for the image of the Batman, you can see that we did it 1, 2, 3, 4 times. So there were 4 forward diffusion kernels in this whole process. Now in this case, we want to do it 8 times. So the number is 8. And as soon as you specify this, what is happening under the hood is the system is applying this formula. The system is applying this formula 8 times. And you might be wondering how are the values for this beta 1, beta 2, etc. designed. So the values are decided internally through this noise scheduler. You can define specific values which they have mentioned here. DDPM scheduler, you can write beta start and beta end, which means that you can specify how the variance is changing with time. So this is something you can definitely do. And one thing we can understand from this graph, I haven't properly explained what this means, is as you increase the number of time steps, you see the cumulative mean goes down and the cumulative variance goes up. That's what we are seeing in this graph. Why does the cumulative variance go up? Because by default, the variance in the noise schedule has an increasing property, so it increases at every time step. And because the square of mean and variance is equal to 1, the mean has to decrease for every time step. Now, what do I mean by cumulative mean? Well, cumulative mean means that if I have a mean of alpha 1 times x0 when I go from x0 to x1, and the scale factor is alpha 2 when I go from x1 to x2. If someone asks me, Rajat, what is the scale factor when you go from x0 to x2? It is simply the multiplication of these means, right? It is alpha 1 times alpha 2. That is exactly what they have done here. They have plotted, and why does the root come here? The root comes here because they are using this notation where everything is replaced by a root. So this is how the mean in the forward diffusion process, the cumulative mean changes with time. It actually reduces in magnitude, and the cumulative variance it increases, because as we go closer and closer to the noise, we want to add as much variance as we can. Okay, so far what we have seen is I want you to focus on these two quantities. The first is this quantity which is known as noise, where we are specifying how much noise is added in the forward diffusion process for each pixel. And later it will turn out that this is exactly the quantity that we are trying to predict in the reverse process. But for now, we should understand that at every time step, we are adding a certain noise level for every pixel in the image. And the shape of this noise is exactly the same as the shape of each image, which is 32 by 32 by 3. Okay, so in fact, it is not by 3. I think it's just 32 by 32 because for every pixel, uh, you're adding a specific noise. And if there are 32 by 32 pixels for a single channel, there will be 32 by 32 different noise levels. And if we are considering three channels, 32 by 32 by 3, then there will be that many noise parameters which you have to consider. So in this case, it will be 3 by 32 by 33, 3 by 32 by 32. Okay, so we have understood intuitively what the noise level means. So whenever I write epsilon in this equation, now you should think back and say that, okay, fine, what I'm doing is that I'm corrupting every single pixel in the image. So I need to know how much each pixel is corrupted by. And that corruption level I'm identifying through this noise value, which I'm manually adding. Okay, so this is the forward diffusion process. That is excellent. What about the reverse diffusion process? Let's go ahead and check it. Now, first of all, the way our model is defined, remember the objective of the diffusion model is to predict the noise level, which is added in the forward diffusion process. We want to predict the same thing in the reverse diffusion process. So, in the reverse diffusion process, what happens is that, so now we know the forward diffusion process in detail, right? In the reverse diffusion process, let's say I am at this time step. I am asked the question, what is the probability that uh, from this time step you are transitioning? So you are predicting what is the image in the previous time step, given the image at the current time step. And you can only find that if you know how much noise is subtracted from the current time step, right? So the reverse process has two inputs. The first input is whatever your image is at the current time step, and the second input is which time step are you looking at. For example, if you are looking at this, then I am at, let's say, in the reverse process, I am at time step equal to 0. Then if I proceed ahead, I look at this image and I am at time step equal to 1. Then I again proceed ahead and I look at time step equal to 2. And for each of these time step, my image looks different. But the main objective is, given the time step and the current image, I want to predict the image which has come before that. So I'm going in the reverse direction. And to do that, people usually use a model which is called as a UNet. Now we have not covered exactly what UNet is in these lectures, because that is not the purpose of this course, which is the principles of diffusion models. But essentially, what we are doing is we are passing an image at the start, which is the current image, and we are also passing the time step. We are passing both these quantities. So the model has the input image. It goes through several blocks of resonate layers, each of which halves the image size by 2. Then through the same number of blocks, we upsample it again, and the final image is that of the same size as the input image. Why is that the case? Remember, finally, we have to predict the noise level which has been subtracted from every image to go to the previous image. And as we have seen, the noise has the same dimensions as that of image. So the unit architecture makes sense for us because the input and the output have the same size. Now, intuitively, why do people choose UNet? It has traditionally worked out to be the best, and even in most of the modern diffusion architectures, you will see the UNet architecture very commonly used. Even in stable diffusion, they use a UNet architecture. I will link link in the description where we have taught UNet very nicely in one of our recent lectures. Okay, so now comes the important part where we are actually defining the UNet model, and this also exists within the diffusers library. So we say that from diffusers import UNet model, and we say model equal to UNet 2D model. Sample size is the image size, which is the input and the output image size. Number of input and output channels are three, we already know. How many resident layers to use per unit block? Two. These are the dimensions of the different output channels and the number of types in the down and the up block. This is largely standard, so you don't have to worry about this too much. Once we have defined the UNet model, we can actually go ahead and create a training loop. Now, this is something that is interesting. The first thing that we have to understand is that whenever we are defining this UNet model, we have to pass two things to it. We have to pass an image and we have to pass the time step. And then the model will predict something which has exact same shape as the input image. So let's try to understand how we train this model. And I think this is one of the most important part of this lecture, because when we are looking at the theory, we don't really get to see the training loop for a practical example. So this is something which will give you a lot of confidence that you have really understood the diffusion theory well. Okay, so the first thing we do is we set the noise scheduler. We use noise scheduler equal to DDPM scheduler. We have looked at this before. Number of time steps is 1000. Number of train time steps is 1000, and beta schedule is, so this is just a scheduler which tells what is the variation in the beta values with time, how fast the variance is going to grow. Remember, we had said that the variance beta increases as the time steps increases and the mean actually goes down, right? Because the sum of the squares is equal to 1. Okay, we use a adam w optimizer in this case, and let's try to understand. The number of epochs are 30. Okay, that's fine. For step and batch in enumerate train data loader, clean images. So clean images is we consider a batch of images. So here the batch size is 64. So we have 64 images in a batch. And this is the noise that we add to each image. Now this is important because this is the noise that we add in the forward diffusion process. And BS is this the batch size. Now this is the step which is the forward diffusion process. What we do is actually the forward diffusion process has already been defined. What we do is in this step, this is the main forward diffusion process, but I will discuss that a bit later after we discuss this. Here what we are doing is that this time steps might be misleading because it might tell you that am I sampling all these 1000 time steps or am I doing something else? So here what we are doing is that we are picking one random time step out of these 1000 time steps, and we are doing it for all the images which are there in our batch size. So sometimes I might pick 100, sometimes I might pick 500, sometimes I might pick 600, etc. We will understand why we are picking a random image. Okay, now have a look at this. So this is where the forward diffusion process actually runs. What we say is noise scheduler dot add noise. So we are starting to corrupt the images, and using one single line we can do that. All we have to do is we have to pass our images in our batch size. We have to pass the noise level at each time step, which is epsilon, and we have to pass this time steps, which is this random random time step which we have selected for each image. So then the forward diffusion process will proceed only till that time step. So here, if let's say I sample 100, right? So I will generate all the noisy images from the clean image till the 100 time step. Now what I do is, I in the next line I actually get the model prediction. So I pass these noisy images to my model, and what I do is I select this time step also, which is one random value, let's say the value of 500 which I have chosen randomly, and I get the prediction of this model. So here I am using the UNet model, and I am directly getting the prediction. So here the idea is like, because you have specified this time step here, noisy images only contains that image which is generated towards the very end. It is the image which is generated at that time step, at 800 time step. And what we are saying is that, given that image and the time step stamp which is 800, can my model predict how much noise has been added to that image so that I can get back to my original image as closely as possible? And to do that, all I do is I create a mean square error loss between the predicted noise and the actual noise. And you might be wondering, why am I sampling a random time step here? The reason this random time step is sampled is because every time you're going through this loop, you're sampling something different. So sometimes you might pick 100, sometimes you might pick 500, sometimes you might pick 600. So eventually in this process, the model learns that, okay, given whichever step I am at in the reverse diffusion process, I can successfully generate my original image by subtracting an appropriate level of noise from that image. So it becomes more robust to the different time steps. So let's say we are converting back from noise to the actual data, and I'm somewhere in the middle. So from that point, if you want to go back, you need to be sure how much noise I need to subtract from that point. That is why this time step values are selected randomly. They keep varying as you go through these steps and these epochs. And then these are some standard loss dot backward, which is the backward propagation, and then we take a step using the optimizer and optimize the loss. So you can see here the loss nicely drops down, and here the noise prediction shape is like this: 40 by 3 by 32 by 32. And here 32 by 32 is because it's the pixel size, and 3 is the number of channels, which is RGB. And I think 40 comes up because I'm using a batch size of uh, 40. Let's try to understand where the number 40 actually comes from. Yeah, this is interesting. This should have been 64 actually, because the batch size which I'm using is 64. Let's see. So the batch size is 64, but I get a tensor which has a value of the first number which I see over here is 40, which is interesting. I will figure this out. If anyone manages to figure it out, please post in uh, the comments below. So this is how you see the plots gradually varying. The loss decreases with time, which is exactly what we expect. And then finally, you can sample from your output and generate images. Now, option two is where we write the sampling loop, which is important for our consideration. In the sampling loop, what we do is we begin with a noise level which is random, and we run through the scheduler from time steps from most to least noisy, and we remove a small amount of noise each step based on the model prediction. So this is the residual, which is at every time step which I am at, how much noise do I need to remove from the model? And then you update the sample with that much noise. This is probably going to have a negative value, and you go to the previous sample. Then you again find the residual. Then you again go to the previous image. So you start with noise and you go to previous images, and this you do 8 times, because you start with 8 images which are completely noise, and then you slowly denoise them and you reach towards the original image. So this is how the diffusion process actually works in practice. I want you to practice tweaking the UNet model, understanding exactly what it takes as an input, what it gives as an output, the dimensions of the output of the model. Once you understand this, you will get much more confident in the theory behind DDPM. And if the mathematics has slightly overwhelmed you, don't worry, you can focus on this practical side of the things more so that you get a more deeper understanding of the concepts. Thank you very much, everyone. And I'm very interested to, I was very excited to talk about this lecture with all of you, because I really believe that practical should be supplemented with theory, at least for some critical topics, so that you develop a very nice understanding of that topic. Thanks, everyone. And I'll see you in the next lecture where we will discuss a completely new framework called energy based models. And we will see how this framework very nicely merges with the framework of diffusion.